Hi, everyone. Hey, let's talk about radiation and radioactivity. Okay, the idea is that there are some atoms out there that have, well, let's just say bad combinations of neutrons and protons. And what's going on there? Well, you remember that protons have positive charges, and the protons are all bunched together in the nucleus, the center of atoms. Well, they're all repelling each other, and they want to fly apart. And it turns out studies have shown that there's a second force in the nucleus called the nuclear strong force. And it's holding all these wiggly protons and the neutrons together and trying to keep them from flying apart. And there's some good combinations of protons and neutrons that allow for stable atoms. They stay all together in one tight nucleus. But there's other combinations. Maybe they have one too many protons, one too many neutrons, or not enough of either one. And over time, they fall apart. It turns out the nuclear strong force is pretty weak if the particles are separated by just a tiny bit of distance. They have to be really, really close for the nuclear strong force to hold them together. Okay, and so what happens when you have these bad combinations of protons and neutrons? You have an unstable nucleus, and it wants to become more stable. So it can do some things to change the number of protons and neutrons in the nucleus. And the result is particles start flying out of the nucleus, and that's what we see as radioactivity and nuclear radiation. Okay, there's lots of different types of nuclear radiation. Here are the three most common types. The first three letters of the Greek alphabet were used to name these common types of radiation. So we got alpha, beta, and gamma, and those are the Greek letters there, alpha, beta, gamma. And so you can use the Greek letters to just kind of represent each type of radiation. And here is what they're composed of. Alpha particles is a cluster of 2 protons and 2 neutrons. So a plus, a neutron, a neutron. And that's a little piece of the nucleus that comes flying out of the original atom. It's fairly large, right? 4 tiny little particles. And so it doesn't travel too far in nature. You can just simply stop it by a piece of paper or clothing. And then this little particle, the alpha particle, has a net +2 charge. It doesn't have any electrons. It comes flying out of the nucleus without anything. And so as it penetrates paper, clothing, or air, whatever it's traveling through, rock, whatever, it can steal 2 electrons from nearby atoms. And, well, what's the atom that has 2 protons in it? So 2 protons means it has an atomic number 2. Here it is, over here on the right. Element number 2, 2 protons, is helium. Yeah, so alpha particles ultimately turn into helium atoms, which are really stable. The next type of radiation is beta radiation. Sometimes you can call it beta decay, beta particles. Either way, a beta particle or beta radiation is an electron, and that comes out of the nucleus. Okay, what's going on? Thought the nucleus only had protons and neutrons in it. Well, it turns out one way an atom can become more stable is to change the number of neutrons and the number of protons in the nucleus. And so a neutron can fall apart. It can decay. So the little neutron, well, has neutral charge. It can split and form a proton that has a positive charge and an electron that has a negative charge. And the net charge is neutral. Oh, and it turns out there's also a tiny little particle called an antineutrino. I think it's Greek letter nu, anti with a little bar over it. Don't worry about that. Turns out that if you add up the mass of a proton electron, it doesn't equal the mass of a neutron. So we're missing a little bit of mass, and scientists have found the missing third particle. It's something called an antineutrino, which is super tiny, has no charge, it's hard to observe, and we're just going to ignore it. How about that? So you have this neutron inside the nucleus. That changes, turns into a proton. The proton stays behind, and the electron comes flying out. Okay, so this beta particle, an electron that flies out of the nucleus, that is smaller than an alpha particle, so it can penetrate far into the skin. So you got to look out for beta particles. However, it's an electron, so you have enough atoms there. Atoms have electrons. They start repelling. Electrons can be absorbed by atoms. Yeah, so it turns out like a 1/2-inch piece of plastic or a single sheet of aluminum foil There's enough atoms there to stop a beta particle, stop a flying electron. The third common type of nuclear radiation is gamma radiation. Gamma rays, gamma light is essentially high energy light that comes out of the nucleus. I kind of like to think of the protons and neutrons wiggling inside the nucleus, and they find a more comfortable spot. They kind of realign themselves somehow, tuck themselves a little neater in the nucleus, and as they relax, they sigh, and they give off light. And this light has a huge amount of energy. It's vibrating very, very quickly, high frequency, high energy. Okay, so this photon, that's another word for light, single particles, if you will, single pieces of light. A gamma ray, gamma photon, that's even smaller than an electron, so it has more penetrating power. So here's a little graphic here. The alpha particles are stopped by paper, but beta particles and gamma rays can penetrate paper, keep on going. You have a sheet of aluminum. Well, the beta particles are stopped by that, but gamma rays keep on going. You've got an inch of lead here. 2.5 centimeters equals 1 inch. And some of the gamma rays might be absorbed, but some of them get through. And so if you're struck with gamma rays, you're hoping they go through. Just keep on passing. In fact, that means your body is transparent to the gamma rays. However, that doesn't always happen. There'll be some atoms that get in the way and try to absorb that gamma radiation, and those atoms will have extra energy. They become reactive, and that's when you can get radiation sickness, radiation damage. Now, these atoms that are kicking out particles, undergoing nuclear decay, they're changing. They're going to change into new types of atoms because they'll change the number of protons. And what we'd like to do is be able to predict what kind of element they turn into. Okay, let's begin with the Greek letters. Alpha kind of looks like a fish. Beta looks like a cursive B. And then what I do for the gamma is I just stand the fish on its head. We said that the alpha particle is 2 protons and 2 neutrons. And we went to the periodic table. An atom with 2 protons is helium. So we can use a chemical symbol for an alpha particle. We can say that, hey, you have the nucleus of helium, atomic number 2. Remember, the atomic number goes on the bottom left. And what's the mass number? The number goes in the top left. Well, that's the total weight. The 2 protons, 2 neutrons, 2 plus 2 is 4. So yeah, so the chemical symbol, or abbreviation, for alpha particles is He24. Okay, a beta particle, we said that's an electron that's coming out of the nucleus. Let's see, if we use the letter E to represent an electron, you're not going to find that on the periodic table, but we're trying to find a spot for it. We're trying to make a symbol for an electron. Well, where does charge go? Charge goes up in the top right, so you can put a minus sign. Some people like to put a -1 up there for the charge. You can do that if you like. And then, let's talk about the mass number. Let's go to the top left number. If we're trying to make this into a chemical symbol, I know it's a little weird, but hang in there. What's the mass of an electron? It's 1/2000th as much as a proton, 1/2000th as much as a neutron. It's pretty tiny. So if you're going to round off 1/2000th to the nearest whole number, what would it be? Yeah, if it was 1/2, you round up to 1. But this is less than 1/2, so you have to round off to 0. Okay, to a whole number, the mass number of an electron is 0. It kind of makes sense. Electrons are pretty light. They don't weigh much, so let's just round off to nothing. Okay, here's the weird part. What's the atomic number of an electron? Well, to go back to the proton, protons have a +1 charge. If you have a single proton in a nucleus, that's a hydrogen atom, and the atomic number is 1, or +1. And there's the key. Down here, the atomic number counts the number of protons in positive numbers. Well, kind of what's the opposite of a proton? A negative charge. A -1 for an electron. Okay, that's weird. But that's what we're going to go with. Scientists have decided that the atomic number of an electron is going to be -1. And there we go. There's the chemical symbol for a beta particle. And I had another student said, well, I get confused. I can't remember if the 0 goes up on top or the 0 goes on the bottom. And someone else in class said, well, just remember that the numbers increase. 0 is bigger than -1, so the 0 goes up on top. Personally, I remember what the mass number means. Mass means how heavy is it. And I remember electrons are super tiny, almost nothing, almost 0. So I put the mass number 0. Okay, it gets easier than that for the next one. Gamma rays, well, for the chemical symbol of a gamma ray, we're going to just use the Greek letter gamma. What's the mass number of light? Light doesn't weigh anything. So the mass number is 0. How about the atomic number of light? It doesn't have any charge. Positive, negative, no. So 0 charge, 0 atomic number. There you go. The gamma ray, the chemical symbol is just a gamma with 0, 0. Okay, and so what we need to do in order to predict what atoms, radioactive atoms, turn into, here's the secret. Let's memorize these 3 chemical symbols. So let's try some sample problems. Here we go. Uranium is radioactive. So we're told here in this question that the uranium is undergoing alpha decay. And the question is, what are the products of alpha decay of uranium-238? What does that mean? What's this 238 sticking there? Well, that's the mass number. So you can go to the periodic table. I think I got one right down here. A portion of the periodic table. Here's uranium from a section of the periodic table. Has atomic number 92. So you can always look up that. But remember down here, this is not the mass number. This is the average mass of all isotopes. And it's just a coincidence that the average is pretty close to the specific isotope that we want. Just coincidence. So if you want to know which atom you have to be told the mass number. And here we are. Mass number is 238. Okay, we're told that an alpha particle comes out of there. What's an alpha particle? Oh boy, got to memorize that. 2 protons, 2 neutrons. We can figure out the chemical symbol is He24. Okay, and then we can reason it out. Try and figure out what did uranium-238 turn into. Well, it starts with 92 protons, and out comes 2 of them. It starts with 238 mass units, and 4 mass units leave as its alpha particle flies out. So the atom that remains behind, the nucleus that remains behind, has lost 4 mass units. So now it's 234. It lost 2 protons. It's number 90. So go to the periodic table and find out what element 90 is. Element 90 is thorium. Okay, what about that shortcut? What are the products of alpha decay of uranium-238? Well, I would grab which element you have, write its chemical symbol. It's U. Look up the atomic number, put it in the bottom left, and then from the question, get the mass number, 238. And then the arrow means change. So the uranium changes. It kicks out an alpha particle. Sometimes I put that over the arrow just to remind myself what kind of radiation we're doing. We're doing alpha radiation. Uranium-238 kicks out an alpha particle. Oh boy, what was the alpha particle again? Oh yeah, 2 protons. 2 protons make up the element helium. Put a 2 down there. How heavy is this helium atom? Well, it's got 2 neutrons in it. 2 plus 2 is 4. Okay, now let's predict what the new atom is after uranium kicks out a helium atom. A helium nucleus, really. There's no electrons here. Well, just do a little subtraction. Mass is kind of conserved to the number of particles on the left side has to equal number of particles on the right side. So if you start with 92 protons and you lose 2 of them, 92 minus 2 equals 90. So the atomic number is 90. And if the total weight of that atom is 238, and you have a particle that leaves with 4 mass units, do a little subtraction there. 238 minus 4 is 234. We'll put the mass number in the top left of our new symbol, and then take the atomic number, 90, here it is, and grab the chemical symbol, TH. Boom, full credit. Okay, let's try another sample problem. What are the products of beta decay of carbon-14? Well, what's going on is that in the nucleus of carbon-14, there's a neutron. This guy right here is going to break down. It's going to turn into a proton that stays in the nucleus, and out will fly the electron and that antineutrino. We're going to ignore that part. Okay, and now the new nucleus has an extra proton in it. So the extra proton, if we start with carbon with 6 protons and we get a new atom that has 7, well, that's nitrogen. There you go. The mass number is not going to change because, we can round off. The neutron weighs about the same as a proton. And now we can say that actually the neutron's a little bit heavier. You have to add in the mass of electron and the silly little antineutrino. But if you round off the whole numbers, protons, neutrons, both have mass of 1 atomic mass unit. And so the total mass stays the same. Time for that shortcut. If we're told to start with carbon-14, then go to the periodic table, find out the chemical symbol for carbon. It's a C. Mass number is followed by, it follows the name, 14 mass units. And then that's going to change by beta decay. We should complete the chemical symbol over here with the atomic number. The atomic number of carbon is 6. Okay, to predict what products are produced after beta decay, you have to remember what a beta particle is. Oh yeah, it's an electron. And now we need mass numbers and atomic numbers. For me, I start with the mass number. Electron doesn't weigh very much. We can basically ignore the mass. It's 0. And then the atomic number, how many protons are there? We have the opposite of a proton. So not a positive one, but a negative one. Okay, time for a little math. The mass number is the funnest one. If you say that everything on the left has to add up to everything on the right, start with a total weight of 14 and subtract 0 from it. 14 minus 0 is 14. So the new thing we're going to make, new nucleus, has a mass of 14. And you got to be a little careful here. You're going to start with 6 and take away this. Start with 6 and take away negative 1. So if you minus a minus, minus a negative number, you end up adding it. So the new atomic number is 7. You know what? The opposite of subtraction is addition. So if the right side has to add up to the left side, you can say 7 plus a negative 1, 7 minus 1, yeah, that equals 6. We can go backwards to check our math. So the new nucleus has atomic number 7. Atomic number 7 means you have a nitrogen atom. And there we go. Gamma radiation is even easier than that. Gamma decay of barium-137. Well, here's barium-137. You could go to the periodic table, look up the atomic number. It turns out to be 56. What is gamma decay? Well, that's when a photon, a piece of light, comes flying out of the nucleus. High energy, so the frequency is very quick. The wavelength is going to be much smaller than this, much tighter. It's going to be vibrating very quickly, lots of energy. And it turns out the protons and neutrons are just kind of reshuffling themselves in the nucleus. So maybe not a good picture. It doesn't look like anybody moved here. I think they do kind of move around. Squirm a little bit, get in a more comfortable position, and release that extra energy as light. The gamma ray has no mass and no protons. So there's no change. Yeah. You just have these elements that are kind of wiggly. They don't change their nucleus. You have the same atom before and after, but the new atom is a little more relaxed. It's lost some energy. It's less unstable. It's more stable now. Okay, here's one more thing we need to learn about radioactivity. Radioactive material gets hot. It warms up. How come? Well, by Newton's third law. So back when we talked about the Newton's third law, every action has an equal and opposite reaction. We had this picture of this guy firing a gun. The bullet comes flying out. That's the action force. And as the bullet comes out, there's a reaction force. There's a recoil where the gun kicks back. Well, same idea in the nucleus. You got this radioactive atom, the nucleus rather, And all of a sudden it's going to kick out an alpha particle if it's undergoing alpha radiation. That goes flying out in one direction. That's your action force. And then there's a recoil. The nucleus moves backwards as this alpha particle gets shoved out. And how's this shoving force happening? Well, as the alpha particle starts to leave, the nuclear strong force that's holding it in place weakens and stops holding it in place. And then the electrostatic force kicks in. The protons in the alpha particle repel the protons in the nucleus. Like charges repel, and that's what's pushing or propelling the alpha particle out of the nucleus. Okay, well, wait a minute. How's this getting hotter? Well, let's think about what temperature is. It's a measure of the average kinetic energy of particles. And after after an atom releases radiation, there's a recoil. The nucleus is moving more. That's more kinetic energy. And so the average kinetic energy is going to go up. Really what happens is the atom starts vibrating. It's probably in a molecule stuck to other atoms. It kicks out an alpha particle and then it starts vibrating back and forth. And as it vibrates, it moves the other atoms around and they heat up. More motion, more kinetic energy, and the material heats up. It turns out that nuclear decay is one source of heat inside the Earth. And after millions and millions of years of radioactive decay inside the Earth, well, the heat energy is not coming out very quickly, and it just accumulates in the center of the Earth, middle of the Earth, and that's enough to melt the rock to create magma. And then once the magma, molten rock comes out on the surface, we call that lava. Why don't I stop now? That'll be the end of part 1 video, and I'll record a second part.